So our next speaker is MacKay, and the title is An Optimal Stopping Problem with a Discontinuous Reward. And
first of all, thanks everyone for being here. I'm very happy to be able to interact with this great group of researchers, and I'm happy to be able to present this today. And again, particularly happy to be speaking after the previous talk, because we're studying the same problem from different, or very similar problem from very different approaches. So I'm excited to be able to interact with the researchers, and also I'm happy that part of my talk will be able to go a bit faster because the introduction was already partially done by the previous speaker. So we're again looking at the problem of the variable annuity. Here, just for notation, the investment account value, which was X in the last one, in the previous talk, I'm using F. And the guaranteed, so I use capital G for the guaranteed amount at maturity. A difference here in the problem that we're looking at is that we're considering a surrender benefit, or a surrender penalty, pardon me. So the penalty could theoretically vary through time, but also vary with the value of the investment account. So that's a first difference that we have. And also the guarantee fee that we're looking into, we consider a more general, bit more general framework where the guarantee fee could vary through time and could also depend on the value of the investment account. And why do we do it like this? It's basically because this problem is something that we had studied previously, but only numerically. And now we were trying to find a more solid, let's say, theoretical basis for what we had done numerically previously. So this is why we have this bit more general framework. Some of the results we were able to obtain them for this general framework, but we also had to restrict ourselves to maybe only time-dependent functions in many cases, but that's what I'll show in a second. So we have this contract, this variable annuity contract, that allows early exercise, and the reward function is the reward function if there's surrender. So if the payout is paid out before time t. Here I have tilde g, general function that I'll give more information about in a minute. And like in the previous talk, the payoff at maturity is the maximum between the predetermined amount and the value of the investment account. Now I went back, I'm sorry. The main characteristics of this problem is that, well, the reward function is time dependent. So when we were working on that theoretically, we were looking at what was done for American options. And I would say that in the actuarial finance literature, when we work with this kind of problem, we really take what was done in math finance for American options, and we have a tendency to just take the numerical methods and apply them directly to our problem. But here, what I wanted to point out first is that when we do this, we overlook these specific characteristics, namely the time dependence of the reward function and the time discontinuity at capital T, which is also something that was mentioned in the previous talk. So like I said, we often overlook this in the numerical, when we do numerical analyses. So now we wanted to look at this a bit more carefully. This is just an illustration to show how, so I think you got it from the previous talk also, but if the value of the investment account is under the guaranteed amount, which here I assume to be just 100, then there will be a jump in the reward process exactly at maturity. In certain cases, if the market performs well, then there's no jump. So this is just some examples from the literature where we looked into this kind of problem from a more numerical perspective. In particular, there's this second one here, this second paper where, this is, okay. The second paper, we looked at a fee structure which depended on the value of the investment account, and we got some interesting results. Again, this was done by solving the free boundary value problem, so the PDE, and we got some weird looking continuation region or surrender region. So in the simple case with a fixed fee rate here, we had a nice enough surrender region. But in other cases, when we started making the fee dependent, especially on the value of the underlying, then we had some weird regions like this. And that was a bit our goal when we were looking into this problem, trying to find, to identify when we have nice, let's say, nicer surrender regions like this one, and when we have these. One thing that I don't like, or that I find more difficult to work with these kind of regions, is that you can see here above 150, it's no longer optimal to surrender. And so if I look just at the section here, let's say at time t equals 15, then I have a continuation. So just for this time, a continuation, let's say, set, which is disconnected. And my problem with this is that for numerical methods, it can be a problem. I can't assume that as soon as I find a level at which it's optimal to surrender, it's always going to be optimal to surrender above it. So that's why it was interesting to identify cases where we knew that here the T section would be connected. So this was a bit the motivation for our work. And I think just in general, the idea of how to manage or how to influence surrender, or in general policyholder incentives using contract design, I think is interesting. So for example, we also looked into let's say a market with stochastic volatility to be able to link the fee rate with the VIX index. This is not going to be discussed in this talk, but I have more questions on incentives created by this type of fee. Yeah. So for the rest of this presentation, this is what I'll go through. So I'll talk about, I think the main tool of the paper is this alternative representation that we have for the value function in our problem. So this is where I want to get to. And then I'll talk a bit about partial answers that we have for the question I talked about before, about when we can have these better behaved surrender regions. The problem setup is very similar to what we saw in the previous talk. Maybe, so what first difference is this fee here. Now the fee that's collected directly from the investment account in order to finance the guarantees. And here we assume that it can change through time, and with also the value of the underlying. So I'll talk in a minute about some examples. And again, the surrender benefit here. So the function G basically identifies or gives the proportion of the investment account of the investment which is returned in case of early termination. And so yeah, so G here would be increasing through time, or at least non-decreasing. And theoretically, it could depend on both the value of the investment account, and of course it it typically depends on time. And the fee structure, I would say, is general enough to include the different fees that were discussed in the literature. So of course the constant fee, which is a very important structure to study, because this is typically what is seen also in the markets. There were some papers on the state-dependent fee structure here, where the fee rate is constant, but only paid when the account value is below a certain level. And there's a time-dependent fee here, where the fee would typically decrease through time, and it can also affect the incentives to surrender. The surrender penalty here, like I said, so the amount that's left or the amount that's returned on early termination, early surrender, will be non-decreasing through time. I want the function g to be in C12, and it has to get to 1 at maturity. So if the person, so just before maturity needs to be very close to 1, so it needs to get to 1 here, of course, continuously. It could vanish, so the penalty on surrender could vanish before maturity. That's not a problem. In reality, certain contracts will have that, where during the last few years, there's no more penalty on early surrenders. Just further definitions for the rest of the talk. I have the discounted reward process here. This is Z. The value function is what I'm trying to, what I want to study. So it's the price of the contract. This is the one that I obtained by solving the optimal stopping problem. And I will say that some stopping time is optimal if by applying this stopping time, it gives me my value function. I'm gonna go through this quickly, but the point of this slide, pardon me, is basically to say that when we first looked into this problem, we didn't know, at first we thought it's just a technicality. We don't need to write a full paper about it. We can go straight to the numerical work. There's probably a paper where our problem is just a special case of the problem studied, and there we can use it to justify using the numerical methods that we used. However, it was not really the case. So a lot of the literature assumed that the reward process was continuous, quasi-left continuous, or regular, and we could not use this. So again, just a few examples where continuity of the reward process for us was a big problem. Or discontinuous was fine, but then we needed boundedness, and our reward process is not necessarily bounded. More recent work by people that are here today, we were not necessarily able to apply either. So what we used in the end was we assumed nothing. We went back to the beginning. We wanted existence of an optimal stopping time. And we found this result in a general paper by Nicolas Caroui, an older paper. And there, we could use these results because they were general enough for this problem. So we used the last 2 papers, and we obtained our stopping time, which I'll get to in a minute. But before I can get the stopping time, I can talk about the stopping time in the general setting. I want to talk about the existence of a trivial stopping time. And this is the condition, because we have the functions G, so the surrender penalty, and the phi function C being depending on both time and the underlying, we get something a bit more complex here, a bit uglier here in this inequality on the left side. But this is basically the function F in the previous talk. I was very happy when I saw this function F in the previous talk, because it seems like what we did was at least partly correct, because we identified the same type of function, which indeed has plays a big role in all of the surrender incentives here, the shape of the surrender regions and everything. And so this is another version of that function F. And when this function here stays positive on the whole domain of the value function, then we know that maturity is an optimal stopping time for the problem. We know that it's optimal to wait until maturity, so not exercise or not surrender early. And the reason here is basically the same reasoning as for an American call option written on a non-dividend paying underlying. And that's our first result. There's, yes, a few remarks. So this is a generalization of something that we had identified in an earlier paper where we were only using a constant fee rate and this type of surrender function. And the idea here is that, well, so here when we have kappa, so the surrender or linked to the surrender penalty. When this is greater than K, then T is an optimal stopping time for one. So these functions here, these phi functions and surrender functions are a lot simpler. And basically this inequality, the inequality there boils down to this one here. And the economic intuition behind it is that basically the expected fee that will be, or the fee that's expected to be paid between small t and capital T, so between, let's say, today and the maturity, then will be less than the early exercise penalty. Whenever I expect to pay less in the future than I will pay on surrender, I prefer staying in the contract. This is really what it says in this simpler case. Now, in general, when we don't have the previous inequality being satisfied, we were wondering, how can we make sure that the stopping time that we've been using for the past 10 years when we were analyzing these contracts numerically, how can we make sure that it's the correct one? Well, El Karoui, and later the result was also written a different way in this other paper here, we were able to confirm that indeed, the first time that the value function reaches the reward process, this is the optimal stopping time. And so this was good for us. So it's the stopping time we were expecting. However, we wanted to analyze a bit more the value function, see if we could, for example, write the problem as a free boundary value problem, everything. But the discontinuity of the reward function was, for us, made this difficult. So we had to find a way to analyze this. And we also wanted to know what we could say about the shape of the exercise region. So that's when we use this alternative representation. What we showed is that if we consider this continuous discounted reward process, so instead of just having the reward here, we take the maximum between the surrender benefit and H. H is basically our quote unquote European option. So it's the present value of the expected maturity benefit here. And it's kind of intuitive, but we had to show it. But if we consider this to be the reward process instead of our original one, which just considers the surrender benefit, we still get the same value function. Okay, so now what we have is we rewrote the value function, but in terms of a continuous reward process. And now all of the nice results that exist in the literature, we can apply to this value function because we have a representation in terms of the continuous reward function. So this is nice. This gives us ways to work with to obtain properties of the value function, and we did that. But it's not necessarily true that the stopping time that gives us this value function are the same. And we're wondering, when do these stopping times coincide? What we get is that in certain cases, they don't coincide at all. They never coincide. Well, these are, let's say, actually, when the stopping time is trivial, when there's no incentive to surrender throughout the life of the contract, the stopping time tau tilde, the one for the continuous time, the continuous reward function, is at inception of the contract, whereas the other one, so the tau, the one from our original value function, is at maturity of the contract. In general, we can show that tau here, the stopping time, the optimal stopping time for our original reward process is basically the one for the continuous reward process when this reward process is stopped, or when the reward is basically this here, the surrender benefit. So when at this particular time, the surrender benefit is greater than the value of the maturity benefit. When this is not the case, then in our original problem, the optimal stopping time is T. So this is how we were able to reconcile the two stopping times. So if we say, well, S is my stopping region my stopping region my surrender region for the original problem, and S tilde is the one for the continuous reward, then when these two regions coincide, my stopping time coincides, because it's the first entry time of the value process inside, the value function in that region. So then we were wondering, basically, when do these two regions coincide? Quickly, I want to talk about, I just want to list some properties of the value functions that we obtained by using the continuous reward process. The continuous reward process, and some more work. So we also get some continuity. Now, this is dependent on our drift being globally Lipschitz. So this already eliminates the state-dependent fee, which is the one that is paid only in a region, because there it has really a jump. However, it does not eliminate all of the state-dependent types of fees. We can still have the fee C be dependent on the value of the underlying, but it just has to do so in a continuous enough way. Okay, so instead of having a fee that's paid in a region, not paid in another region, we could have a continuous function that brings the fee down to 0 in the region where we don't want it to be paid. Then if we put more assumptions on our fees and surrender function, basically if we remove the dependence on the value of the underlying, then we're able to get some, to study, Lipschitz continuity in time and in space of the value function a bit more. And this allows us to, have more results in terms of, can we express this as the solution of a free boundary value problem and everything like that, which is what we did. So we have that under some, again, mild continuity assumptions, we have that V is the unique solution to a free boundary value problem. And to us, this was important just because it's a problem that had already been, that we use, let's say, this representation to come up with numerical procedures to solve the problem. So we just wanted to check that everything was correct there. Same thing for the variational inequality. So just transferring everything from the American option, not everything, but some of the results from the study of the American option to this problem, to make sure that when we apply them directly when we apply the numerical methods directly to the variable annuity problem, that what we do is correct. Now, I think to finish, I just want to say a few words on what the optimal exercise or surrender region looks like. So a lot of our results, we had to restrict ourselves to the case here where both the fee and the surrender function depend only on time. In certain cases, we're able to go to the more general case, but not always. So some of the results that I present here, they can actually apply to the case where, especially like C here, could also depend on X in a continuous way. But for now, I'm just going to restrict myself to the time-dependent case. We got the integral representation here for the value function, just like in the previous presentation. So we also got this integral representation, which is, to us, it's analogous to the representation for the American option. So here, the E, we call it the surrender premium. We also have, so this is basically the value of the European contract, or present value of the maturity benefit plus the surrender premium. And we have the continuation premium representation, which basically says that the value function can be expressed as the surrender benefit, the surrender benefit plus another part here. So the F, some expectation and an integral part. This was useful because what we have is this term here and that term here. This is basically the simpler version of the more complicated equation that we had. This coincides with the function F from the first talk. We call it function L here. So this term and that term, when they are positive or negative, it really impacts the shape of the surrender region. And this is what characterizes a lot of the surrender region. And we see that it's really, like was mentioned previously, it's really the interaction between the fees and the surrender function. And so what we have is that, again, just for time-dependent fee and surrender functions, if we look at the T section, so if we fix T and we look at what happens just in terms of S, what we have is when this function is always negative, then we can say that there will be an incentive to surrender. Okay, it will be possible to, or it will be optimal to surrender at some point before maturity. And when it will be optimal to surrender, so it's not clear that for every time T will be optimal to surrender, but when it is optimal to surrender, then the T section of the surrender region will really be of the form BT to infinity. Okay, so it will not be, it will not be optimal we won't have this problem where it's not optimal, then it's optimal to surrender for some values, and then above that, it's no longer optimal to surrender. This is not the case here. So, and this is only when this function here is less than 0. And in this case, we can also see that both surrender regions for the original problem and for the continuous reward problem, then they coincide. However, when this function is positive for some T in an interval, then for this interval, it will never be optimal to surrender, basically. So the surrender region is empty on this interval. What we have here, so we just looked at fee functions that depend on time. We have, again, a surrender function that looks like what we had in the previous talk. And we get some weirder surrender regions like this. Here it's optimal to surrender at the beginning of the contract and towards the end, but in the middle, there's no incentive, or it's not optimal to surrender optimally, or to surrender. Same thing here. So again, this is really due to the time dependence of, I think part of it is due to the time dependence of the fee. So that also helps being able to eliminate the surrender incentive. Yeah, and that's all I had to say today.